your homework out from last night, the worksheet that I gave you guys. Okay? And whether you wrote those on paper, whether you did it online, doesn't matter, but we're going to go over the answers here in just a couple of moments. I'll give you guys a second to get it out, and then we'll go over it. All right, that sheet will be for much later on in the day today when I'm teaching you guys some new stuff, okay? So just put it aside for now. We'll come back to it later. And for those of you who are joining us online, of course, the handout that I will be referring to today, I will give you guys on Thursday when you come to class, okay? But it will be useful for you today if you will go on to the Google Classroom stream and find the section entitled Polyatomic Ions, Naming and Formulas. Okay, if you go onto the Google Classroom stream, you're looking for polyatomic ions. Yeah, you guys don't need to do that because you have the sheet. But the kids online, since they don't have the sheet in front of them, they're going to need, and that's right there with today's date. You notice 10/27, the assignment that I've given you for today, that section is just above it, polyatomic ions, naming and formulas. That'll take you to the CK12 book, and you'll be able to use the polyatomic ion list that's in the textbook there, okay? And again, when you come to class tomorrow, I'll give you your very own copy of the polyatomic ion sheet. Okay, so let me just go through these problems super quick. I'll start with, I don't know which side is technically side 1 and which side is technically side 2 because I just printed it off and I didn't have page numbers on it when I typed it up. So I'll just start with the side that says sodium oxide, I guess. Okay. So at the top it says sodium oxide, and I've asked you to write formulas. Okay. And so, I think I probably need to move this a little bit. Hang on a second. That'll probably be better for you guys at home. Okay, so sodium oxide, we're going to write the formula here for this compound, and that means writing the element symbol for sodium, capital first letter, lowercase second letter, and then of course we have subscripts in there to balance the charges. That's what we worked on yesterday. And so I need a 2 after the sodium, and then the capital O for oxygen. So if I were to just read you this formula, which is all I'm going to do for the rest of these, okay, it's going to be Na2O, all right? And so again, anytime there's a number, that should be written as a subscript. So aluminum chloride should look like AlCl3. Magnesium nitride is Mg3N2. Gallium sulfide is Ga2S3. Lithium fluoride would just be LiF. Calcium selenide is CaSe. Rubidium phosphide would be Rb3P. Boron iodide is Bi3. Strontium arsenide is Sr3As2. Potassium bromide is simply KBr. Cesium sulfide is CS2S. Beryllium iodide is Be3Ag. I2. Barium oxide is BaO. Sodium iodide is NaI. And calcium fluoride is CaF2. Any questions on the first side? All right, on the second side, number 1 is calcium nitride. Number 2 is potassium iodide. Number 3 is gallium bromide. Number 4 is lithium oxide. Number 5 is boron phosphide. Number 6 is sodium arsenide. Number 7 is cesium chloride. Number 8 is aluminum oxide. Number 9 is magnesium iodide. Number 10 is barium phosphide. Number 11 is rubidium sulfide. Number 12 is beryllium fluoride. Number 13 is strontium selenide. Number 15 is magnesium oxide. And the last one is lithium nitride. Any questions from anybody on those? Good. All right. Fantastic. All right. Today, we are going to learn basically 2 new things today. We're going to look at transition metals. We haven't looked at those yet. Okay. So we're going to be forming transition metal ions, much like we did last week, late last week, when we did metal ions. And we're going to name them. And then we're going to put them into compounds and practice naming compounds with transition metals, okay? And then the second thing that we're going to do is I'm going to introduce you to, you might have guessed, polyatomic ions, okay? And then we will name compounds that contain polyatomic ions today as well, okay? So those are the things that we're going to be doing. Here we go. Let's start with vanadium. Find vanadium on your periodic table. It is a transition metal, D block element. I would like for us, I got a note here. Lexi, I just saw your note. Okay. Yeah, I think once you submit it, you can't see it anymore. So just be careful of that. If you're be careful about submitting, especially those practice assignments. If you notice that it didn't have a no grade associated with it, that means I'm just going to go over it in class. Okay, so for future reference, don't submit those until we go over them. Okay, so vanadium, I would like to write its electron configuration. So I'm ready when you are. Oh, watch out. How many? Good, excellent, Karen. Okay, thank you, sir. Well done. All right, here is the electron configuration for this element. My next question to you all is, how many valence electrons does this thing have? 2. Yes, 2 is good. Where are they? The 4s, right? So think about your atom here, right? Remember that the coefficient numbers are basically our concentric circles, right? So we've got 1, 2, 3, 4 concentric circles, okay? The one farthest out is this one. And now granted, we would put electrons based on the off-ball principle, we would put electrons in here before we would go back and continue filling in on the third ring because it's higher in energy. Even though it's closer to the nucleus, it's harder for electrons to go in there, right? Okay, so we're filling this in first based on, again, energy, off-ball principle. But the 4s, that's the farthest electrons from the nucleus. So that's the valence electrons, all right? So if it has 2 valence electrons, and knowing that most atoms want to follow the octet rule, right? They want 8. So what do you think this atom is probably going to likely do to get stable?
Give away.
Yeah, absolutely, right? So it's going to give them away, and that will make its charge wonderful. +2. All right, and your assumptions there, ladies and gentlemen, would be right on the money, okay? However, and this is why we waited until today to do transition metals, till after you practiced with the main block elements and started feeling very comfortable with them, all right? The transition metals behave very oddly. You see, because they are filling in their d sublevel electrons, okay, they behave differently than the main block elements do, those metals in groups 1 and 2 and 13, all right? And they will give away not only their valence electrons, but they're also kind of willing to play nicely with whatever element wants to bond with them, and they can give away some or even all of these d electrons, okay? And so that being said, we would expect vanadium to have a charge of 2+, but it also could give away 1, 2, or 3 electrons from its d sublevel, meaning that it could also have a charge of 3+, 4+, or 5+. Okay? And so when we want to name transition metal ions, we have to be able to have a way to let the audience know which charge is the appropriate charge based on what's going on. And so chemists have decided to use Roman numerals. By the way, side note question, do you guys know your Roman numerals from 1 to 10? I should write them on the board real quick. Okay, so just a side note, again, Roman numerals, 1, 2, 3. This is 5 minus 1, so 4. 5, 5 plus 1 is 6, 5 plus 2 is 7, 5 plus 3 is 8. And then this is 10 minus 1, which is 9, and 10. That's kind of the way Roman numerals work, okay? So if you don't know those, jot them down. You'll need to use them, okay? And so if you think back to the main block metals that we named in terms of their ions, we just called it the sodium ion, the magnesium ion, the calcium ion, the aluminum ion, right? Because they always give away the same number of electrons. The group 1 metals always give away 1 electron. Group 2 metals always give away 2 electrons. Aluminum always gives away 3 electrons. Are you with me? But the transition metals will do different things. So when we name them, we use the different Roman numerals to basically say how many electrons were given away, okay? So if vanadium only gave away its 4s2 electrons, it would be called the vanadium 2 ion. So we would use that Roman numeral 2 with its name, okay? Of course, if it gave away any of its d electrons, then we would put the appropriate Roman numeral in here that we need, either 3, 4, or 5, respectively, right? Depending upon how many electrons it gave up, okay? And so, again, with the transition metals, we must use a Roman numeral to indicate the charge of the transition metal. Now, For the sake of my class, because I'm so loving and generous to you guys, I will always either tell you the charge or I will make it so you can figure out the charge, okay? So it'll never be a mystery to you, okay, unless you choose not to learn what I'm teaching you, and then I can't help you. That's your choice, okay? But I will always either tell you or make it so that you can figure it out, all right? Now, I need to pause here for a moment. Got that down, gonna get rid of that stuff. And we need to talk about some exceptions. All right. There are 3 transition metals that we will deal with. That was important, okay? So for my class only, there are 3 transition metals that always behave the same way every time. Just like the group 1 metals always behave the same way every time. Just like the group 2 metals always behave the same way every time, okay? These 3 metals will always behave the same way every time. So let's take a look at what's going on here. Find zinc on your periodic table. Its electron configuration ends in 4s2, 3d, 10. You all agree with that? Okay. So, how many valence electrons does zinc have?
2.
Yes, only the 2 in the 4s sublevel. Okay. Now, how many electrons does the d orbitals in total hold?
2.
Yes. So the d sublevel is completely full. And not only is the d sublevel full, but in filling the d sublevel, the 3rd energy level is now completely full, right? So that makes zinc very, very stable there. So the only electrons that it will ever give away are those 2, meaning that it always has a charge of
+2.
There you go. Okay. So zinc always has a +2 charge. Therefore, we don't need a Roman numeral with it. Okay. Where's cadmium on the periodic table? Yes. So it ends in 5s2, 4d10. It's right under zinc, right? Guess what? It behaves the same way zinc does. So cadmium also is always 2+. That's part of the reason why they're in the same column. They behave the same way, right? We learned that already about elements. When they're in the same family, they tend to behave alike. And that's because of their electrons. Now, what about silver?
47.
What's its ending electron configuration?
5s2, 4d5.
Good. Okay. How many electrons does D need to be full? 10. Just like this, right? So when silver reacts with other elements, it always does this. It will always take one of its electrons and put it into the D sublevel, filling that up. Now, how many valence electrons does it have?
1.
Only 1. So silver's charge is always +1. It only has 1 that is willing to give away, because the 1 will always go into the D sublevel to fill it up. All right, so these 3 elements, ladies and gentlemen, memorize them. Okay? Memorize their charges. Silver's always +1, zinc and cadmium are always +2. It's important that you do that because you cannot write a Roman numeral, nor will I ever give you a Roman numeral. You just have to know its charge, okay? So memorize these 3 elements. But wait, that's not all. I got a deal for you. There are 2 elements in the main block of the periodic table. Now, the main block elements we've been working with for several days, and we've never used a Roman numeral with them, correct? But there are 2 elements in the main block that behave like transition metals, meaning they can have multiple charges, tin and lead. Where are they relative to each other?
They're on top of each other.
Same group, right? So we would expect their behavior to be similar. All right, and tin and lead can both have either a +2 or a +4 charge. Okay, so don't just memorize these 3 elements, memorize these 2 as well, because they are the only main block elements that we'll deal with in my class where you have to have a Roman numeral with them, okay? So, no Roman numeral, transition metals. Must have Roman numeral main block elements. So it's kind of the exceptions to the rules, right? So the rule is the transition metals need Roman numerals, except for these 3 in my class. And the main block elements don't need Roman numerals, except for these 2 in my class. All right. Now, if you guys are lucky enough to get to take more chemistry in college, thank you for smiling. That was cute. Okay. But if you're lucky enough to take more chemistry in college, you'll learn more and there will be more rules. Okay. But for this class, this is enough. This will be good. All right. So let's practice. Let's do let's start with this one. Here's the name. I would like for us to write the chemical formula. What is step 1?
Finding them.
Okay, find it. Where is it?
24.
All right. And of course, you know to look in the transition metals because it's got a Roman numeral and it's not lead or tin, right? So you look in the transition metals and we find it. What's its symbol? All right, Cr. Do we know its charge?
Okay.
You're getting warmer. Keep going.
+3.
Yes. It is +3. How do we know it's +3?
Because it's Roman numeral.
That's what the Roman numeral tells us. It tells us the ion's charge. Okay? What's this?
Sulfur.
Do we know sulfur's charge when it becomes an ion? -2. How did we get -2? How many valence electrons does it have?
2. So it only has 6.
6. It wants 8, right? So it's going to gain 2 more. That's where we get the -2 charge. Has 6, wants 2 more to get to 8. Okay? So I've got my symbols for the 2 elements. I've got my charges for the 2 elements. Now we just have to balance those charges out, right? In other words, one way to think about this is we've got to find the least common multiple of these 2 numbers. What is the least common multiple of 2 and 3? 6. So I need to get to 6 plus here and 6 minus there, right? How many chromiums will it take me to get to 6 plus? 2 of them. 2 times 3 gives me 6, yeah? How many sulfides does it take me to get to -6?
3.
3 of them. Again, 3 times -2 is -6. So the formula is Cr2S3. Any questions? Uh-oh. I obviously need to turn my computer up because I am not hearing that you guys are leaving me messages. I didn't hear it. Okay. No, or do some. All right, FeCl3. Of course, this time I've given you the symbols for the elements. In other words, I've given you the formula, right? So we need to come up with the name of this compound. So step 1, find Fe. What's its name? Is it a transition metal?
Yeah.
Then it's going to need a Roman numeral. So leave a space for it. Okay? And may I suggest, guys, you're taking notes, right? You're writing things down. And so, you know, I'm just trying to help you guys learn how to take good notes, okay? So a good thing to do right now is to jot a little note. Leave a space for the Roman numeral. Because we're going to come back to it in a minute, you know? So jot yourself a note, leave a space. And then let's continue on. What's this part over here? Chlorine, but we have to change the ending to IDE, so we'll write chloride. Okay. All right, we need to figure out the Roman numeral. So we're going to begin here. Okay, watch what I'm going to do. We're going to start here. So I write, you know, I write the cation name, I leave a space for the Roman numeral, I go to the anion, and then I continue with the anion up here. How many valence electrons does chlorine have? Good. It wants 8, so it will gain 1, giving it a charge of -1. All right. How many chloride ions were used? 3 of them. So the total negative charge is 3 minus. How do I get that? -1 times 3 is 3 minus, right? So I essentially took the charge and I multiplied it by the number of ions. Are you with me on that, okay? So my net charge, the total negative charge, is -3. Now, in order for the formula unit to be valid, the charges have to balance out, right? So if this is -3, this has to be +3. Okay? Do I have a subscript here? No, that means that this iron then contributed the entire charge. So the charge of this iron ion is +3. Okay? Yeah, I'm going to do another one. Yep. Yep. All right, first step. What is this? Cobalt. Is it a transition metal?
Yeah.
All right, let's leave a space for the Roman numeral. We'll come back to that. What's this? Nitrogen, but it's in a compound, so nitride. All right. We're going to follow the same exact procedure we did moments ago, okay? Start with nitride. How many valence electrons does nitrogen have? 5. Needs 8. What will it do? Gain 3. Therefore, its charge is? Okay. How many nitride ions did we use? So what's the net negative charge? Okay, negative 3 times 2 is negative 6, right? And now again, the compound has to be electrically neutral. That's what a formula unit means. So if we've got negative 6, we must also have positive 6. But that positive 6 is distributed over 3 different ions. So if we multiplied this way, we're going to divide the other way. So what is my 6 charge divided over 3 ions? So this is cobalt 2 nitride. Cobalt 2 nitride, okay? Any questions on, any questions on the idea of doing the transition metal ions? Okay, good deal. All right, so you guys are going to get some practice with those tonight. Okay, read the section. I think it's section 6.11 if I remember correctly. And that will, again, give you just more exposure to the forming of the transition metal ions, how they get their charges, and it'll list a whole bunch of the different ions with the different charges that they can have, just so you can kind of be exposed to them. That's why I assigned to that section. Okay, now the next part is where those of you who are online with us, you're going to want your textbooks. Again, go to that section called Polyatomic Ions, Naming, and Formulas. Okay, and for those of you in the class, it's time for the pink sheet. Okay, so again, guys, at home here, I'll give you all a pink sheet when you come to class on Thursday. So a few things that I want you to notice, whether you're looking in the book online or whether you're looking at the sheet in front of you. These things, these lists are usually broken down for us very nicely. Typically, they're broken down by charges, which is true. First column's -1, second column's -2, third column's -3, 4, and 5, et cetera, okay? Typically, they're also alphabetized, which it is. That's wonderful. So it's very easy for us to kind of begin to find these things, knowing that number one, it's alphabetical, and then secondly, of course, it's by charges. Thirdly, for those of us in class today, and when you guys get your copy at home on Thursday, you'll notice that on this list, some of these are in bold print, okay? And the bold ones are the more common polyatomic ions, the more kind of everyday stuff, if you will. So those are the ones that we'll be using more often than the others. Not to say we won't ever use the others, it's just that we'll use the ones in bold more often, okay? So what is a polyatomic ion? Well, let's back up and kind of begin to answer that question by talking about what we did last week with monatomic ions, right? The word tells us everything we need to know. A monatomic ion is an ion made from one atom, right? Monatomic ion. So a polyatomic ion, of course, is an ion made from many atoms, okay? And they are just a group of atoms that work together, and they have a charge, and they got that charge by either gaining or losing electrons, okay? Just like our monatomic ions did. And where might they have gained or lost electrons from? Well, some other ion. So for example, in the case of this ion, it needed an electron for all these atoms to be stable, working together. Where did it get that electron from? Maybe sodium, for example, because sodium has an electron to give away, right? Okay, so the formation process is essentially the same. Sodium would give away its one valence electron. Then the nitrogen and 3 oxygen atoms that are all bonded together would accept that one electron. Then everybody here has 8. This has 8. We're all happy, okay? Getting very dry, talking a lot today. Okay, so again, we have one nitrogen atom bonded, covalently bonded, by the way. We're going to talk about that next week, okay? But covalently bonded to 3 oxygen atoms, and in the process, somehow, those 4 atoms gained this electron. Now, you simply look on the polyatomic ion sheet, and this thing has a name. What's it called? Find this on your polyatomic sheet. What's it called? Hint, it's in the first column. Alphabetical.
Nitrate.
There we go, nitrate. All right, so the first thing that I want to point out is the ending, okay? Notice it ends in ATE. Many of the polyatomic ions end in ATE. And those that end in ATE have oxygen in them as a rule of thumb. And watch this, there's one right above or below it, and it looks very, very similar, but it's NO2. What is that one called? Nitrite. Notice it ends in ITE. The 8 ending implies more oxygens. The ite ending implies fewer oxygens. That's a general rule of thumb for these ions. So if you look through the list, you'll find, for example, sulfate and sulfite. You'll find phosphate and phosphite. And it's always true that the 8 has more oxygens than the ite does, okay? So that's the endings are ATE and ITE for most of the polyatomic ions. Now, check this out. There are a handful of polyatomic ions that end in IDE. Uh-oh. That could be trouble because we're already doing IDE endings, right? But here's the thing, it's not trouble. Look, here's your periodic table. There are literally a handful of monatomic anions. Look on your periodic table with me. They are nitride, oxide, fluoride. You with me? Phosphide, sulfide, chloride, arsenide, selenide, bromide, iodide, astatide. That's it. Okay? So if it ends in IDE, we can look first at the periodic table and see if it's any of those elements. If it's not one of those elements and it ends in IDE, where will we find it? Somewhere on this list. Okay? Now, the interesting thing about the polyatomic anions that end in IDE, How are they differentiated? Why are they different than the 8s and the ites? Well, these guys, generally speaking, don't contain oxygen. Okay? So, for example, here's one. Cyanide. Notice it doesn't have oxygen. Ends in IDE. Okay? And that's true. Most of the polyatomic anions do not end in IDE unless they have no oxygens. So the oxygens end in H and ite, and no oxygens end in ide. Okay? But again, you look on the periodic table in that upper right-hand corner, and we can't find an element that starts with the prefix cyan. Right? There's no element cyan. So we know it's not monatomic. It must be somewhere on this sheet. Must be polyatomic. All right? Okay, so when we name the compound, again, we're just going to put the anion and the cation together. It's a 1-to-1 ratio because the charges are already balanced, right? +1, -1. So this would just look like NaNO3. And the name of this would just be sodium nitrate. Very, very simple. This part, we just look up the name on the polyatomic ion list, write it down. Easy peasy, lemon squeezy. Okay? Not hard at all dealing with polyatomic ions. Now, there is one caveat that I need to make you aware of. Please look in the lower right-hand corner of your list. Lower right-hand corner. I want you to circle ammonium. NH4 plus. Circle that ion. I've already asked you guys to do a lot today, but here's one more thing. It is in your best interest to memorize this ion because it's the only polyatomic cation that I will use in my class. Okay? Only polyatomic cation that we will use. So if you don't memorize it, you probably aren't going to recognize it, and it's going to mess you up when it comes time for us to name compounds that contain that thing. All right? And I don't want you to lose points because you didn't memorize this ion. So it's in your best interest to memorize that one ion. So let's just do a couple of examples, and then I'll give you guys the rest of your class time today to work on some practice problems. So let me go ahead and throw one out here. Let me make sure I spelled that right. And I should make sure that that is the right charge. Yep. All right, we're going to write the formula for manganese 4 oxalate. First thing we got to do, of course, is find manganese. Where will I look? We want to narrow our search. Where do you know you have to look to find this thing? Transition metals. Thank you. That's what I wanted to hear. It's in the D block. Okay. So find manganese. What's its symbol? Mn. Good. What's its charge? Uh-oh. +4 is correct. How did we get the charge of +4? That's right. That's the number in the parentheses. Our Roman numeral tells us the charge. All you got to do is look on the periodic table for the symbol with the transition metal. The charge is right here, okay? You'll get used to it, but you better start soon or you'll have lots more struggles than you need to have, okay? So the charge is right there. It's the Roman numeral. Charge of manganese is +4. All right. We need to write down oxalate. Where do I know to look? Where am I going to look to find oxalate?
On the pink paper,
Yes, how do you know it's on the pink paper?
because it's ATE.
Right on. Ends in ATE. That tells you immediately you know it's on the paper. Or for you guys, it's in the CK12 book on section on polyatomic names and formulas, okay? So what does oxalate look like? C2O4. What's its charge? Negative what? Yeah, how did you know it was -2?
It says it right there.
Thank you, good answer. Says it right at the top of the column, right? These are all -2 ions. It also tells you next, with the formula, but sometimes kids get a little bit confused, especially like with the -1 charges. They'll see nitrate NO3 minus, and they won't make sense out of the fact that that's not a 3 minus charge. It means there's 3 oxygens and it's a -1 charge. It's in the first column, it's just got a negative charge, okay? All right, so now I've got to balance the charges, right? What's the multiple of 4 and 2? I heard somebody speak, but I didn't catch what was said. 4. Yes, both 4 and 2 can be divided into 4, right? So I need +4 and I need -4 in order for those things to balance out. You with me? You understand what I'm saying? Okay, so how many manganese ions does it take me to get to +4? Just the one, it's already there, has a charge of +4. How many oxalate ions does it take me to get to -4? 2 of them. What does that look like? 42. Do I really want 42 oxygens? No. What do I want? I want 2 oxalates, right? So there's a very logical way that we do that in chemistry. Think about math class. This distributes to what's inside, right? So this means that I have 2 of whatever's on the inside, okay? So whenever you have a polyatomic ion, if you need multiple of them, use parentheses, put the subscript outside after the parentheses, okay? By the way, just to make sure that we're all geniuses in class today, which I'm confident we are, how many carbons do I have here total? 4. How many oxygens do I have here total? 8. Very good. Just want to make sure we were all on the same page there. All right, so there we go. If I've given you the formula, or excuse me, I've given you the name, you can determine the formula, right? You just need your periodic table, your polyatomic ion sheet, do a little bit of easy math, middle school math, by the way. That's when you probably first learned about least common multiples, so we can handle that. All right, and then let's just do one where we go the other way, okay? So let me give you a formula, and then you tell me the name. This is that part of me where I like to be mean. Because I always like give you the hardest thing you can possibly come up with. But at least I'm doing it as an example, right? Okay, so what have I got going on up here? This is definitely a far cry from the binary compounds that we worked on end of last week, right? Definitely a far cry from that. But this is very simple because we're still doing ionic compounds. Therefore, I have to have a cation and I have to have an anion, right? Okay, well, until today, every cation was always what kind of element? How would we classify all of the cations? What kind of element were they? There's only 3 kinds of elements. Uh-oh. You guys are making me nervous. What are the 3 kinds of elements? Yeah. There you go. Thank you. Good. Metals, nonmetals, and metalloids. So the cations, until today, have always been which one of those 3? Metals. Right on. Very good. Okay. Are there any metals up here? What if there's a metal? Uh-oh. Let me know when you're ready. I mean, if you want to change your answer.
No.
Good answer. No, none of those are metals. You guys know where the metals and nonmetals and metalloids are, right? I assigned those sections to you. You should know this. All the metals are way over here. This stair-step line separates the metals from the nonmetals, and the metalloids are the ones that touch the line, right? So we've got nitrogen. That's over here. We got hydrogen. Well, that's over here, but it's a gas. And we talked about that the other day when I talked about hydrogen and the alkali metals. Is it a metal? Hydrogen? It's a gas at room temperature. No, it's not a metal. It's in group 1 because it has 1 valence electron, but it's not a metal. Carbon, is that a metal? No. Here's hydrogen again. Oxygen, is that a metal? No, these are all non-metal elements, right? Okay, so there's no metal cation up here, but that's what we're working on. I'm not throwing you a curveball. This is an ionic compound. So if it's not a metal cation, then it has to be the polyatomic cation. And do you see why I want you guys to memorize this one? Because if you don't recognize it, you'll get this wrong every day of the week and twice on the weekends. So what is an H4? Ammonium. That's the one I want you guys to memorize. So make sure you spend time working on that today, tomorrow. Get it memorized. You'll want to. And then what is C2H3O2? If this is the cation, the rest of it has to be the anion, right? So what's C2H3O2? You should have found it by now.
Lactate.
There we go. It's the very first one on the list, okay? And it's pronounced acetate, all right? Acetate. So this compound is named ammonium acetate, all right? Again, it's new, but it's not hard. You just have to look up the polyatomic ion names and put them down. It's just a matter of recognizing you got to, and that's going to come with practice. That's why I'm giving you guys practice. As you use this sheet, you'll see these polyatomic ions. You'll get used to them. In fact, before you know it, you're going to have a lot of them memorized. Okay, you'll know not only the formulas, but you'll even know the charges if you're really working hard and doing your homework that I ask you to do and reading and all that jazz. Okay, you just got to find those polyatomic ions. So again, here's what we did today. Well, actually, let me back up. So last week and yesterday, we were writing and naming monatomic ions and binary ionic compounds. Compounds with only two elements, a single cation and a single anion. And until today, those binary compounds only contained main block elements, right? So today, we added the transition metal elements. What's special about them? What's new now with transition metals? Roman numerals. Those are the two words I wanted to hear. We got to use Roman numerals with the transition metals, and the Roman numerals tell us the charges. Very good. Excellent. Okay. And then once we practice, we'll get comfortable with those Roman numerals and figuring out the charges. Okay. And then, of course, finally, the last thing we're doing here was introducing us to polyatomic ions. And again, these are not hard. We just have to begin to recognize them. So use the sheets, study over it a little bit, do the practice that I asked you to do today, and you'll get used to that. So our assignment for today, there's two things with today's date on it on the Google Classroom page. Today's 10/27. The first assignment that you should see there is a reading section. I think it's 6.11 if I remember correctly. Okay, and that's just going to go through the transition metal stuff for us again. And then the other thing that I have for us is I found a really good website that's going to allow you to just practice, and it has binary ionic compounds with both main block and transition metal ions, and it has polyatomic ions. And it tells you right away if you're right or wrong. I love that, right? Because I'm not at home with you to check over your work tonight. But the website tells you right now, did you get it right or did you get it wrong? So then you can try to figure out if you got it wrong, obviously, okay, I made a mistake. Can I figure out what I did wrong and can I fix it? Okay? So the only other thing that I really want to mention is don't forget with the polyatomic ions, if you need more than one ion, parentheses, right? I got to say that before we're done. So go to that website. It has two different places for you to practice. It has practices naming and it has practices formula writing. And I think there's like 12 options on both places. And so make sure you practice all 12. And after you finish with the names and the formulas, if you're not super comfortable, go back to the names and do them again, and just practice a little bit until you get comfortable. Okay. And then I do want us to meet together tomorrow afternoon just for a few minutes. It'll be a short meeting, but I do want us to meet tomorrow afternoon. I'll give you some instructions, and I've got an assignment for you to work on tomorrow. So make sure you come to the meeting at 1:45 online, those of you in the classroom. 1:45, we'll have a short meeting, and then I'll have work for you guys to do. So if you guys online have any questions, I'll stick around and answer them. Otherwise, you all are free to go and get to work. And of course, you guys can get to work here.